Hello, everyone. Let us review what we learned so far. Then we're going to talk about a new technique to solve iterated integrals, in this case, double integral. So recall them. Recall that we said, well, if we have a function in two free variables, then to integrate this function, we need double integral. One integral doesn't work because we have two free variables. We use double integral to find, depending on the question, the volume, it might be the charge, it might be the density, it might be related to probability, the density function, volume, density, charge, and so on. Well, we said that, okay, when it comes to double integral, if the region that we are taking the integral over is a nice region, what do we mean by that? A rectangular region, then we can just take the integral and change the order of integration. So if the region is a rectangular region, remember the definition of rectangular region R equals to the set of points like X and Y such that X is bounded between two fixed numbers like A and B, and Y is bounded between two fixed numbers like C and D. We can represent this guy by bracket A, bracket B, cross bracket C, bracket D. This guy represents a rectangular region in the plane. So the visualization is going to be like this. You have X, Y, Z, and this is your region down here. Well, this is a rectangular region that we have. This is our region. And then, so this guy gives me the area, the base. If you're thinking about the volume, you already have the base, you only need the height. Well, where is the height? Here we have our surface on top. This is my surface, whatever it is. This is Z equals to f of X and Y. Then, well, we're going to have the same thing, but it might be curved on top, and it gives me the height. And we define our double integral this way. Double integral of the function, it's the height. It stops at the ceiling, dA over region R, which can be defined as double integral f of X and Y dx dy. If you are taking the integral with respect to X first, your X ranges between A to B. So this is your inner integral. This is what we learned. We first take the derivative, take the integral with respect to X. And then we take the integral with respect to Y, C to D. We have to be careful about the ordering. C, D. And note that we said that, hey, if we have a rectangular region, we can switch the order. It doesn't matter. These two are fixed numbers. X is in between fixed values. Y is in between fixed values. So it must be equal to double integral. Again, you have your height, function Z, f of X and Y. Now you can take the integral with respect to Y, then with respect to X. So since you're taking the integral with respect to Y first, Y ranges between C to D. So this guy is going to be your inner integral, your first integral. Then you're going to take the second integral, which with respect to x, a to b. Now remember that we need to all of those techniques of integrations that we learned in elementary calculus. If you don't remember those, please check your Canvas. There are some prerequisite videos posted for you. There's a cheat sheet of all of the integrals that you need to know to be successful in this part of the course. Well, we said that, okay, what if my base is not in rectangular form? What should I do then? It happens that sometimes your x is fixed between two values, but your y is changing. Or your y might be between two fixed values and your x is changing between two functions. In those cases, it's super important for us that the outer integral has fixed boundaries. If the region is not in rectangular form, it might be either the case that your x is bounded between a and b, but your y is bounded between two functions, gx, hx, or your y is bounded between two fixed values, c and d, and your x is bounded between two functions, g of y, h of y. Okay. Since your x is fixed between two numbers, this guy must be the outer integral. The outer integral with respect to x, and we just quickly write it down. Then the inner integral is with respect to y, gx, hx. Well, whatever the function is, you have dy, dx. The order of integration is important. This guy comes first, taking the integral with respect to y. Then we take the integral with respect to x. However, if our y is fixed between two numbers, two fixed boundaries, this guy goes outside. The outer integral is going to be integral with respect to y, c to d. We quickly write this down. The inner integral is with respect to x, so gy, h, y, f of x and y, dx, dy. So this is my inner integral, my first integral, then I have my second integral. Last time we saw examples that if we switch between x and y, we might end up with more complicated boundaries. So if you have complicated boundaries, try to switch your variables. If x is bounded between a and b, y is bounded between g and h, and you see, okay, now I have a complicated double integral to work with. Try to convert that into y bounded between c and d and x bounded between two functions. You might get a double integral, which is easier to calculate. Very well. Now we have this issue that what if we have a region that includes circle or part of a circle? Very well. I'm going to write one example and explain what's going on here. So this is the example that we're going to work with. This example says, well, here, evaluate evaluate the double integral of 3x plus 4y squared dA over region R, and they define this region this way. They say that, hey, this region is upper half plane, or is the upper half plane bounded by the circles, bounded by the circles. Okay. Circles, what circles? X squared plus y squared. One of them is just the unit circle, and the second one is x squared plus y squared equals to 4. So you have unit circle with radius 1, and the other guy is circle with radius 2. Remember that when we try to solve these types of problems, our very first step is to try to visualize what's going on here. Step 1, graph the region. Okay, graph the region. So this region is in XY plane. X-axis, Y-axis. Remember that what information are given to us, read the question carefully. It says upper half plane. It means that I'm not working with the lower half plane. My focus is on upper half plane, where Y is positive. This guy is unit circle. Okay, unit circle is not very hard. I already know the unit circle has radius 1, and this is my x squared plus y squared equals to 1, but in upper half plane. The second one is x squared plus y squared equals to 4. It means that I have radius 2. Remember to convert this into the format that you see radius 2. Okay. Well, minus 2 and 2. Not a nice one, but let me fix that. There we go. So it says bounded between these two. It's like a washer. So this is the area that you are looking at. So remember, this guy is in the plane. So you can just convert this. You have your x, here you have your y, and here you have your z. Well, this surface, whatever it is in the space, whatever that guy is. This is your z equals to 3x plus 4y squared. Down here, you have your region. Where is that region? The region is located here. This is the region that you are dealing with in XY. So then your job is to find the double integral and using the height. Okay, using the height, it's going to be something similar to this, for example. And then, so this is your, this guy reflected here on the surface. Suppose this is this format. Of course, it has some changes because it's the ceiling on top. And then you find these, all of these little heights, and you're looking for either the volume, depending on the question, whatever is asking. Is it the volume? Is it the density? Is it, charge? Whatever it is, you're going to find this double integral. So this guy represents the double integral. Well, what they say that since this region has the elements of a circle, we're interested in using the polar coordinates. So in general, if the region is a circle, or half a circle, or it has some elements of a circle, some part of it, some slice of circles, or slices of circle, we use x equals to r cosine theta, y equals to r sine theta, and we convert the double integral to an integral with r and theta. Then we convert the double integral which is double integral over region R, f of x and y dA to the double integral over region R, which is now converted into f of, guys, x is r cosine theta, substitute that here. R cosine theta. Wherever you see x, you have to substitute that by r cosine theta. And your y is r sine theta. Wherever you see y in the function, you have to write r sine theta. And your dA is going to be, well, this is the important part that we have to remember. Your dA is going to convert now into r dr d theta. R dr d theta. Don't forget to add r as the element of radius here. We are converting our region into polar coordinates, x r cosine theta, y r sine theta, and instead of dA, into the formula, we're going to have r dr d theta. So let us use the new formula for this example and try to solve this. Very well. Step 2. Convert x r cosine theta, y r sine theta, and dA is r dr d theta. Okay, let's see. R as the radius ranges between 1 to 2. R is in between 1 to 2. This is the radius. What about theta? Theta starts from 0. It starts rotating and stops at pi. So your theta is in between 0 to pi. Very well. Do I have all information? Yes, of course. Step 3. Double integral. Here you have your function. Let me erase this part of the board. I need more space. My f of x and y is now f of r cosine theta, r sine theta. So I have 3 times x. What is x? X is r cosine theta. R cosine theta. Plus 4 y squared. What is y? Y is defined as r sine theta. Y is r sine theta. So let us write this down, and we have to raise it to the second power. R sine theta to the second. Well, don't forget about your dA, which is now r dr d theta. So let's put this guy in parentheses, r dr d theta. Well, r, as we know, bounded between 1 and 2. So this is my r. R is bounded between 1 and 2. And my theta is bounded between 0 to pi. 0 to pi. Zero, 2 pi, not 2 pi. Okay, here we go. Well, as usual, let me erase this part of the board and solve the rest for you. Very good. So again, R is bounded between 1 and 2, and theta bounded between 0 and pi. I said pi, but I wrote 2 pi. Please correct that. It stops at pi. Well, so let us solve this guy. Well, okay. How do we solve this integral? Let us try to simplify this first. We have integral 0 to pi and 1 to 2. Here we have 3r cosine theta plus 4r squared sine squared theta r dr d theta. Well, here we can just distribute r into parentheses. We get integral 0 to pi, 1 to 2, 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Well, let's take the integral with respect to r first. This is our inside integral, first integral. It's not very hard to find the integral with respect to r. Well, here r to the second, r to the third, and theta acts like a constant. So this is the integral 0 to pi. Well, here you have r cubed cosine theta plus r to the 4th sine squared theta, and my r is bounded between 1 to 2, then d theta. So this guy is equal to the integral 0 to pi. Here we have, if I plug in 2, I get 8 cosine theta plus 16 sine squared theta, and minus, if I plug in 1, I get cosine theta minus sine squared theta d theta. Well, okay, I can simplify this. 8 cosine theta minus cosine gives me 7 cosine theta. And then 16 sine squared minus sine squared gives me 15 sine squared. Well, now we are taking the integral with respect to theta. Cosine is not very hard, but what about sine squared? So remember that. To find the integral of sine squared theta d theta, first you have to use half angle formula and convert this guy. This is equal to the integral 1 minus cosine 2 theta divided by 2. Let me see. So here we have sine squared plus cosine squared, and here we have cosine squared minus sine squared. So we get rid of cosine squared and cosine squared, and we're left with sine squared. So for this integral, we have to write it as 1 minus cosine 2 theta first. So let me just put a star here and put 1 star here for you. Okay, so this guy is equal to integral 0 to pi. So the first integral is not very hard. Let's just write this guy down. Here we have 7 sine theta, and here we get plus 15 divided by 2 theta. And here we have minus 15 divided by 2 sine 2 theta divided by 2, and theta ranges between 0 to pi. Very good. So if I plug in pi, this guy is going to be 0. If I plug in 0, these two are equal to 0. And again, 15 over 2 times 0 is 0. So what's left? Here you have 15 pi divided by 2. Make some of the co-hosts. Very well. Let's go over another example. So this is how we get the RD theta, because we have the sector of a circle and the area of a sector is a half theta r squared. Well, if you take the derivative, it's going to be a half d theta to r dr, because it depends on r and theta. Well, in the very small case, so dA is equal to r dr d theta. That's how we get the element of integration in double integral for when we're using the polar coordinates. Let's go over another example, everyone. So in this example, question says, well, yeah, this case here